All of the descriptions of Le Chatelier's principle that you just saw were very qualitative, whether it was adding or removing, thinking about temperature, pressure, volume, or even a catalyst. It was about recognizing which side of the equation was that favoring or impacting, and how is it going to get back to the equilibrium it was at. We can also do this in a quantitative sense, or we can connect it directly with Q and K, because when we add a reactant or add a product, we are actually changing the initial amount that we would be putting in our Rice table, or that we would be plugging into our equilibrium expression. So when we increase a reactant, we would remember that that would be on the bottom, the numerator of our equilibrium expression, which would then make Q smaller. If Q is smaller than K, that's because we have too much reactants, we have not enough product. When we think about K as that P over R, product over reactants, we can really think about, to get to the right value, to get to the correct ratio as described in the problem, which thing do I need to have more of? We also have right here, if I decreased a reactant, well, now I have less of the thing on the bottom, so that has the opposite impact. We can also put in some of a product, maybe our initial amount, or maybe we were at equilibrium and we threw it off. Well, that would make our K bigger because products are on the top. I have too much of a product. I need that to go down or decrease. I need to get my Q equal to my K. In both of these, and even when we change the pressure or the volume, the reaction shifts to return to the same K. Adding or removing a chemical, adding or removing pressure, increasing or decreasing the volume does not change the value of K. It's a very common, both multiple choice and free response kind of trick question. When I add or remove this, what does it do to the reaction, shift left or right? What does it do to the amount of maybe one of the chemicals? And we would think, well, have I made more or have I consumed more? But then lastly, the trick lies in, what does it do to K? And sometimes we default to thinking, if I have made some product or consumed some product, K changes. That's not true. Remember, it's shifting to get back to K. But in actually the largest font in this whole section of notes, changing the temperature does change K. That's because, as it says right here, temperature impacts the two major things that determine what the equilibrium position should be. It impacts the energy of the system, and it impacts the organization, disorder, and what we call the entropy of the system. So at a new temperature, our products or reactants actually become more or less favorable. They don't just shift one way or another, they kind of shift that way and they would stay that way. So higher temperatures favor things that absorb heat. We looked at that right there. It shifts right, but it stays shifted right. It's not trying to get back to that same K. It's establishing a new K with more products, so that would end up with a higher K value. A low temperature would favor reactions that release heat. So if I took away my heat, then this one would shift right, raising my K. And the questions for these can kind of be a cause and effect either way, or the information, data, or observations they can give you could be either way. It could tell you that it's endo and exothermic, ask for the effect of changing temperature. It could give you the temperature change and ask for then and tell you that something increases or decreases, and asks you to predict and justify whether it's endo or exothermic. It could give you that it's endo or exothermic and want to know what happens to the amount of something based on a change of temperature. So remember, reactants, products, concentration, pressure, volume, none of those change K, but temperature does change K, because it shifts and stays shifted as we change the energy and the entropy of the system.